This is a pre-built version of the application. So let's go ahead and run it. So we'll have four peers. And they would be running in peer-to-peer mode. And this will be the driver peer. And the other three will be trying to find the shortest route. So when I don't specify the mode, it defaults to solve mode. And this peer will be picking up messages from all other three peers. And each one of the other three will be picking up messages only from the driver peer. So all three non-driver peers are waiting for requests from the driver peer. And so the driver peer wants to find the shortest route, and it can use any one of the 6 algorithms that we have here, either a brute force or a genetic algorithm, or simulated annealing, or hill climbing, or nearest neighbor, or ant colony optimization. So let's start with genetic algorithm. And each one of those found the shortest route and returned it. So using genetic algorithm, the shortest route found by this user on this peer had this distance, and this is that shortest route. And this user on this peer found the shortest route with this distance. So this one. And same for this user on its associated peer, it found a shortest route with this distance using genetic algorithms. So let's try with simulated annealing. So same thing, each one of those other peers did the simulated annealing, used the simulated annealing algorithm, and found those 3 routes by the 3 different peers. And same thing if we use hill climbing, we get those three routes, and if we use nearest neighbors, we get also those three routes. And if we use ant colony optimization, we get those three routes by the three different peers. So using ant colony optimization. And now let's try using brute force. So here we have 8 cities, and if we notice here, we only did permutations, actually here. So here we only we have 8 cities, but we only did permutations for 7 cities, and we don't see it since we are not running in verbose mode. So each one of the peers returned 2 shortest routes that it found, and all of those routes are actually the same. So here if we go New York, Houston, Austin, LA, and here so New York, Houston, Austin, LA, San Francisco, etc., and San Francisco, Denver, Chicago, Boston, New York, and the other way around, San Francisco, LA, Austin, Houston. And I'll run one with the verbose mode so that we can see that each one of the peers only do permutations for 7 cities if we have 8 cities. Same thing if we have 9 cities, we only do permutations for 8 cities. So each one of the peers does a different permutation and returns its result to the driver peer. And here if we send an exit, they all exit. Now since we have 8 cities in the hard-coded data, I went ahead and created 9 different peers. One of them will be the driver peer, this one, and the other 8 will be trying to find the shortest route, and they will be using brute force to do that. So each one of the peers will be doing a permutation of 7 cities. So this one will be picking up messages from all peer, the driver peer, and all other peers will be picking up messages from the driver peer. here we can find the shortest route, and if we do that, we can use brute force to do that, and so each one of the 8 peers found its set of shortest routes, two of them. And they end up all being the same or equivalent. So if we start from Austin, Houston, New York, it's the same as Austin, Houston, New York, Boston. Or we can go Austin, LA, San Francisco, etc. And same for the other. So we ended up with 16 cities, 16 routes. And let's exit. And I want to show that we can run in standalone mode. So we'll do, let's do verbose and standalone, and we'll do brute force. So here we go. And those are the same that we found when we did peer-to-peer, except it will take shorter time, since each one of the peers will only do 7 permutations of 7 cities, and find the shortest routes among those 7 cities, and then add the starting city and find the shortest route for the 8 cities. And we add the starting city at the beginning. And we can do a genetic algorithm and simulated annealing, and we can use a different data source. So we can use a database and play in verbose mode, and maybe do so standalone, and we can do hill climbing. So in the database we have those cities, and we can do nearest neighbor, and let's do else, and maybe change the data source, use file, and let's do and colony optimization. So we'll run in standalone mode and colony optimization. So this is the shortest route we found, and from file we have those cities, Canadian cities. And just to show the permutations on each one of the peers that are trying to find the shortest route, I have 4 peers here. This is a driver peer, and this is the 3 peers that are trying to find a solution. And the driver peer will be picking up messages from all 3 other peers, and each one of those three peers will be picking up messages from the driver peer, and they all are running in verbose mode. So let's find the shortest route with brute force. So here we got 8 cities, but each one of the peers did permutations of 7 cities. And then added the starter city and found the shortest route. So this number of permutations, 7 factorial. For each one. And we found each one of the peers found those solutions with this distance in miles. Now the source code will be available for download. Also a longer version that includes the coding and test running of the application will be available for viewing by channel members at the senior developer level and above. So this one can send an exit message for all the others.